And hello OpenFoamers, welcome back. So we want to continue our discussion and validation of the heat transfer coefficient, especially Nusselt number. Okay, so first thing first, we want to calculate what's the experimental Nusselt number versus the temperature. Okay, so temperature instead of time will be our metric of measure. So I'm going to copy down the temperature first and the heat transfer coefficient. So surface temperature, and I want to start by using the OpenFoam heat transfer coefficient, which is this area average, which is fine. So I paste the data values. Open heat transfer coefficient. Okay, all of these are in the correct units. I mean SI units. Okay. So what is next? Recall that Nusselt number. Yeah, I can't remove all that. I can't remove all the data. I'll just when all this is finished, then I'll probably want to upload this in GitHub, and of course clean up all the data here. Might as well can do it now. Okay, so probably you probably have to run this on your own computer, and then yeah, you'll be done. So I'll just do it all clean here. Just get rid of everything. So you just gotta go and do it yourself. Yeah, you can get it from the GitHub. Yeah, once this is done. So okay, let's go. Last Nusselt number, HD over K, right? And this is the Wikipedia page for Nusselt number, and this is the, remember K here is the thermal conductivity of the fluid. So right, we take the free stream thermal conductivity value, which is at 300 Kelvin. What is the thermal conductivity value? Okay, so again we have K, and then we have a D. Diameter is 3 cm, so 3 over 100, and K will be, well, we have to get it from our thermophysical properties and look for a 300 Kelvin thermal conductivity value, which I think you have to take a look here. 300 Kelvin is somewhere between 15 degrees and 405, obviously. Okay, so thermal conductivity is here. So we can either do linear interpolation, or since we have since we already have this values that are being calculated in Excel, K would be roughly about 0.13. Yeah, so this is the correct graph here. K is a Daltham, or I just use the word oil. Okay, so this is the K of the oil, and K, this will be in degrees Kelvin. So K, I will have it as 0.0002 times 300 plus 0.1856. So K is 0.1256. I'll just copy that and paste here. Okay, paste the value.
It wouldn't matter that there is drift if the solid.
Okay, where is it? Paste value. Yeah. So okay, I'll just put it here. So K equals to 0.1856 minus 0.002 times 300 equals to 0.1256. 56 watts per meter per Kelvin, and it's a meter times Kelvin. It's not a millikelvin. Okay, so I'll just put a bullet there. D equals to 3 over 100 meters, and we'll just do a Nusselt number calculation. straightforward there.
But I guess what I'm saying
Oops.
is that like
Sorry.
the
Okay.
temperature and the solid temperature.
I think, yeah, I'll just copy and paste, cut and paste it here. Let's do a Nusselt number versus temperature.
You know?
Okay, okay,
And so like how would we want to do it
alright.
knowing that?
So,
Will we just correct both of them to be
this is a function of T surface, not T fluid, yeah? So it's the H times D, log this, divide by
like
K
if you
fluid.
do the method that you just
So
described
H fluid
to correct
will be changing, D and K will be constant, at least in the bulk fluid. So because we always use the bulk fluid temperature for that kind of correlation. So Nusselt number around 18 it looks like, HD over K. And then the Nusselt number is decreasing, etc. Okay, that's part 1. Next thing we need to look at, next important dimensionless number. Okay, I'll just, next important dimensionless number is the Prandtl number. Prandtl number is mu Cp over K.
and let's say that after that is done,
Okay,
like the two of them still don't
Prandtl, okay.
then
Let me put a bit of title here. Nusselt number versus temperature.
better. Well,
Okay, let me do K fluid.
The data that
Yeah.
we have for like
Need presentation and D of the sphere.
Oh, right.
And now I want Prandtl number
So
of the fluid at 300 K.
you'll make is not going to be exactly correct, and so
Okay,
they'll still be a little bit off.
TF equals 300 K.
No, well,
Alright,
so that's the point of doing
so
the
Prandtl number.
calibration first.
Prandtl,
Because if you do that
and if
first,
you put type
and
a
then you
spacebar, it will give you this kind of funny thing because PR also can stand for probability.
oh, I
Okay,
see what you're saying.
mu Cp
You're
over K.
saying-
So let's take a look at the thermophysical data again.
Okay.
So K is 0.1256. That's convenient because we already calculated that. Let's take a look at Cp
Calibration
of the fluid.
error. But you're saying
Okay, and we have a viscosity reading as well.
maybe it looks. Oh, sorry. Maybe it looks like this.
Okay, but let's look at specific heat first. Okay, it's this very long
Maybe this was
thing, and of course we have viscosity,
You got the calibration
which
error?
I think,
Yeah.
I hope it is dynamic viscosity. Okay, so according to this website, Engineering Toolbox, oil has a dynamic viscosity,
And then
10, or olive oil at least, 10 to the minus 1 Pascal seconds. So Pascal seconds is the correct unit for dynamic
Well,
viscosity, not kinematic viscosity.
you
So
have another one,
just make
Well, I know
the
in the book
differentiating
it's one,
factor here,
but
dynamic viscosity. So what I need to do is just, well, I can technically just read it off this graph, but yeah, probably can use this polynomial as well.
right. But you're kind of you have
Okay.
a target incentive.
So
Target is
okay,
getting it to like
let's put the temperature 300 Kelvin.
seeing what the average value is.
All right, so I will have 6 terms.
I have two
So, yeah, like
assignments
the
due
thermal
tomorrow, and I wanted to go to the office hours.
So
Yeah.
okay, it goes to minus
One or two,
5e minus 17
But also you're
times
and
this to the 6.
might not get you
So that's the first term. Second term
because
equals minus 1 e minus 13 times
your goal is
times temperature
then
to the 5th.
like this,
Third term
and right on top.
equals to 2e minus 10 times temperature to the 4th.
Start out here.
Okay, fourth term. Okay, this is 1e minus 7 times temperature to the 3rd.
Start out like
Oh, it's a minus 1e minus 7.
And then from like the
And then
data set where we do the
fifth
calibration test,
term,
it tells you to shift it down
5e minus 5 times t squared,
right? There's some
sixth
separated.
term
Yeah.
equals
And then
minus 0.00.
give you
So,
this.
okay, let me zoom in. Don't squint my
But there's still
eyes.
a little bit.
Minus 0.0095
Like the drift direction will only flatten them out, but it won't make them
times temperature.
Right. So basically, right.
So remember, squared, third, fourth, fifth. So I'm looking at the power here. So it's 6th power, 5th power, 4th power, 3rd, 2nd, 1st, and then the constant. 7th term.
So this doesn't really.
So that will be 0.7894.
So maybe what we could do is say like
7894.
transfer quasi-substitute
Okay.
first.
So
Make our first step.
I don't want to type everything out. So I'll just do alternate equal. Okay, no. I'll just do sum like that.
We attribute like all
And that will be a negative number?
between those
That's
two
very strange.
at that point.
6th term, 5e minus
We can
0.0095.
thermocouple recalibration error. That's something you can measure. Right. And so we
Okay,
can't
5e minus
we can only
5.
attribute the calibration error by
Okay, I think I got a mistake here. Hold on. Oh, I see. In my 3rd term, I had a typo. So I just have to put times there instead of n.
I think I'm convinced that this is a rabbit hole not worth
Okay, good.
burrowing into. Like,
Let's see if there's any other typo.
This is why frequency response is like the way forward.
Dynamic viscosity is about 1 point something.
Like
I got it
you're-
really off.
if we're dealing with this
3rd
transient
term.
system,
Okay, let's try the 3rd term again. 1, 2, 3, 2e minus 10.
it's not straightforward. And I think it suffices.
Okay, hold on. Okay, I think I know why. There was not enough significant figures in this thing. So let me change according to scientific.
I agree.
Yeah, and give it 4 decimal places.
To try and correct it.
Right, or maybe 3.
I think it's enough. Just explaining that.
Okay, hopefully that solves things, and hopefully that doesn't change too much of my k value. Well, the k value seems really precise anyway, so scientific. Okay, minus 1.60 times 10 to the minus 4. 1.6 e minus 4. Alright, so I have a higher k value. I have to do some counter correction here.
Model error.
Okay, there you go.
So let's just call it that instead of
Put 0.1376. Yeah, let me just quickly make that correction.
And so
1376.
we set this to be like some small number.
Okay, so that's a lesson for
Basically what you will
for me. Okay, but just a reminder, please take note of your significant figures. Apparently this is a pretty important thing, so
So
Yep.
would you still want to
make learn making mistakes. But yeah, anyway, so first term,
model error and how much of it is
and I think I know what to do now. Instead of this, just make it a little better. T power and a constant or coefficient.
using the data set of thermocouple calibration error. And anything that's left
Okay.
over we could attribute to periodic differences.
Power n. Okay,
Or
so
not
t to the power 6,
the thermocouple
t to the power 5, t to the power 4.
Why is that?
Oops,
Because I don't think it's like significantly
power 4 goes to t 3 t. Okay, t power squared goes to t. Oops, here and equals 1. Okay, I'll show you what it does shortly, but this will allow me to just copy and paste a lot of the things here. So You can even do 5 decimal places, that doesn't really
Don't
matter.
wanna do that, or if it does, if it changes
Okay,
a lot,
so what I can do,
then you might
copy and
have to
paste,
have,
1,
like, different bins. And then check is
okay,
what
let me
kind
try
of
again,
range you're in,
copy and paste, yeah,
a little bit of a pain.
yep, that's one, second bin, second one, copy and paste. I can do away with all the manual typing,
But yes, I
which
actually
probably we want to
agree
avoid as much as possible.
this is not
This
something a lot of math.
third term, and that will actually reduce the mistakes.
Kind of explain
And this in the fourth term,
that relation.
this in the fifth term,
Yeah, it would also be good because we're trying to finish
number 6 is here,
experiment. Yeah, good to be able to move on to that. Yeah, exactly. I don't think we
and seventh will be this one.
can erase this.
Okay.
For some reason, when we leave things on the
And the dynamic viscosity will be the sum product. Okay, this is a sum product. That means of these two. What does the sum product do?
I was just gonna go home,
Sum product
grab the notebook,
basically,
find it.
excuse me,
I've got a midterm.
sum product basically goes this times this plus this times this plus this times this times this, and you just add everything up there. I think the sixth term I made a mistake. There should be a negative sign there.
One on Wednesday.
Okay, and that will give you the correct dynamic viscosity here. Okay, so I will just copy and paste into Word. Okay,
For Bernstein's one-on-one midterm, there was like one extra credit.
alright, so that I'll just paste it as a picture so that you can, see what the dynamic viscosity is. Cp, mu at 300 Kelvin equals to 0.00375.6. Okay, Pascal seconds. Okay,
Somehow I got him paid.
yeah, so that's mu, and we can do exactly the same procedure for Cp. Cp.
I mean, I know about
Okay, 300k. Mu will be 300k.
what's the difference between screen and
So mu,
so the screen is
so we have the dynamic viscosity ironed down. We can just copy and paste this over here.
Yeah. And
Control V again to give it the what do you call that? Just paste the values. It's very nicely done. So okay, next thing we want to do similar kind of a pattern is CP. So again, I have to do this. I have to change the number into scientific, and then I'll give it 4 dps, 4 decimal places. And let me shift the chart here, or maybe I copy and paste the chart here. So I'll just duplicate the chart and specific heat capacity CP, and I want the temperature at 300 Kelvin again. So again, I'll have these coefficients and terms since it's already being done like that. Okay, so okay, it's only up to the power of 4, so these two I can cancel out. So these are 5 term, this is a 5 term thing, so the first two I can actually delete because I don't really need that. So this is actually t to the 4, t to the 3, t to the 2, t to the 1, and a constant. So what we can do, simply copy and paste, since we spend so much time writing that down. Copy 1, second one,
Well, I would agree with that if it wasn't limited to the number of times. Like if it was like
second one,
you get one freebie, like everybody
Third
comes
one.
in and takes these 7 tests, and then based on how you did on those 7 tests,
fourth one,
Seven's a lot though. Like, what if it was like 5 or 6 max?
and the fifth term
If
will
there
be
were
the
any that you,
constant.
like, knew you just
1
didn't
point
want,
something 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 times to the
Like, I would've-
third.
Like, I didn't take
Then we'll have the
I think they should
heat
let you choose
capacity
how many
in
you
joules
take.
per
Like, you
kg
can
per
say
Kelvin.
You have to pass 4 at
CP
least. You can take up to 7 if you'd like. And
They
there's
know
joule
no
they
per
restriction.
kg
No,
Kelvin.
there is.
Oh, there
I asked if, like, if you fail one, can you take a different one maybe next time? It's the tests are hard enough that unless you did a nuclear undergrad,
So
you
CP,
wouldn't want to take more than 4. Like, I wouldn't have had a chance on
okay,
the ones that
it's
I didn't take
1591.1103 joules per kg Kelvin. Alright, so 1591.1103. So that is a trend line. That's the polynomial fit CP in SI units will be here. One copy and paste here.
Yeah, and then the
Control, I'm
fusion
sorry.
one,
Control V,
I would've- yeah,
Control
I
V
would not.
and paste. Control V again. So that's Control V to paste and Control and V to paste data. So now you can do the Prandtl number, which is mu CP over K. Okay, so mu, where's mu? Dynamic viscosity, log, times CP, log using F4, and K. Again, I log using F4. This will be the Prandtl number. Okay, Prandtl number. Okay, I mean just to be a little, yeah, I think this should be good enough. Hopefully. 1856. Okay, maybe I'll give it a 4dp. Yeah, it is pretty straight. So Prandtl number is about 43 for this this level. Okay, so we have the Nusselt number changing, we have the Prandtl number. Last thing we need is a Grashof number, which I will continue talking about in the next video. So thanks for watching. I'll see you guys next time. Bye bye.